Okay, this is going to be the video for section 4.7 for differential equations, which is about Cauchy-Euler equations, which are a particular form that are not well solved with other methods, but occur frequently enough that they have their own method of solution. This is the last of the units the sections in chapter 4. So the variation of parameters method that we learned recently here, that will always work if you have linear differential equations with constant coefficients. But then when you divide through by the leading coefficient, sometimes you get a result which has functions. The coefficients on the left-hand side are functions of x. Sometimes that can work with variations of parameters, but frequently it will not work unless the constants on the left-hand side are all constants, or the coefficients are all constants. So we have this other method that will work with a subset of cases that don't work for variation of parameters. And this works for a class of differential equations which are known as Cauchy-Euler equations. And so a Cauchy-Euler equation is one where you have coefficients on the left-hand side and a function on the right. These functions are either constants or these coefficients on the right-hand side are either constants or are functions of the independent variable, x in this case, right? But then there's this special requirement that each coefficient contains a power of the independent variable whose integer power matches the order of that derivative. So if you have a second derivative term, you'll have an x squared and then just a constant in that, right? And then the first derivative term, if present, would have a constant times x to the first power, okay? And this could continue for other orders as well, but if you have that where you have an x to the power that matches the order of the derivative for each term on the left side, then it's referred to as a Cauchy-Euler equation. Okay, so for differential equations in this form, there are actually two different related procedures that we could use to solve for the complementary solution. And then we can use the methods like variation of parameters or undetermined coefficients to find the right-hand side. Okay, so, and again, these are fairly complicated as to why they work. So I have included a separate PDF that talks about the derivations for section 4.7. So we're just going to use the procedures here. Okay, the first method, which is used more frequently, and does this. It says, first of all, take the equation and put it in the standard form for a Cauchy-Euler differential equation, which has all the derivatives lined up like this, and then we label the constants of each of the coefficients a, b, and c. If this is a second order equation, then we can use this thing called the auxiliary equation. Like we did before, we're going to solve for what values of m make that 0, and then we're going to use standardized forms for how to use those numbers in the solution. We'll have different cases for distinct real roots, repeated real roots, and complex conjugate roots like we did before. The difference is for a Cauchy-Euler equation, because these are not constant terms, right? There's an x squared here and an x. We have to use a different form of the auxiliary equation. So it turns out that the auxiliary equation form we have to use to solve for the roots is am squared plus the quantity b minus am plus c equals 0. So a little bit more complicated than the regular auxiliary equation. Okay, but we solve for the zeros, and then that will result in some combination of roots of the auxiliary equation. If we have two distinct roots, we'll definitely have two because this is used for only second order differential equations, right? Then the first one is going to be some constant times x to the first root plus some constant times second to the x root, okay? Or sorry, x to the second root. And note, this is important to note. In this version for Cauchy-Euler equations, it's not e to the mx, it's just x to the m, right? So not e to the mx, not this, like we did in the earlier auxiliary equation form. So it's x to the m. Okay, and then if we have one real root that's repeated, then, in this other case, we did e to the mx plus we tacked on an x and then e to the mx. But here, since we're already using powers of x, it's going to be c1 x to the m plus c2 x to the m, and what we're going to multiply by is the natural log of x, okay? Okay, and then if you happen to have complex conjugate roots where alpha is the real part and beta is the imaginary part, then it's c1 x to the alpha, not e to the m or alpha x, it's x to the alpha times cosine of beta, but the beta is multiplied by natural log of x. Okay, and then we also have a term for the same form except with the sign included. So like before with the auxiliary equation, we have memorized patterns, but the patterns are a little different. Mostly they involve x to the power instead of e to the mx, okay? Okay, so that's the first method. The second method involves substituting x equals e to the t. And if you go through what that substitution looks like with the chain rule and everything, you can do a series of substitutions which will convert the original differential equation into a differential equation that always has linear, it's always linear with constant coefficients, which can then be solved with earlier methods. So you have an equation in this form, a Cauchy-Euler differential equation form. If you substitute x or e to the t for x, that's the same as converting t's into natural log of x, right? And it turns out then that all y primes end up having to be substituted with 1 over x dy dt, and all y double primes are substituted with 1 over x squared, and then this quantity, second derivative of y with respect to t minus first derivative of y with respect to t. So a lot of stuff to try to memorize. We don't use this method as much, but we'll do one example with that. So when you do that substitution, it turns out that you'll convert to a linear differential equation with constant coefficients that we can solve. But in the end, then, we're substituting, we now have t as the independent variable. So when we're done, we have to resubstitute that all the t's are really natural logs of the original x to express the solution in terms of the original independent variable x. All right, so let's take some examples. This first one, we'll use method 1 on. So this is in the right form. It's got to be ax squared second derivative plus bx first derivative plus cy equals 0. So it looks like my a is 1 here, my b is -2, and my c is -4, right? So then you have to use the memorized form of the auxiliary equation, which is am squared plus b minus am plus c equals 0. So in this case, it's going to be 1 times m squared plus b is -2 minus 1 times m plus c, which is -4. And so we're going to end up with m squared minus 3m minus 4 equals 0, which can be factored into m plus 1 times m minus 4, which gives me m is -1 and m is +4. So we have two distinct real roots. And that means that our solution here is going to be a constant, but not e to the -1x, it's x raised to the -1 plus c2 times x raised to the +4, okay? And in this particular one, this was homogeneous, but that would be the full solution because we didn't have a right-hand side to go further. All right, so that's how we use method 1. Let's take another example, a little bit more complicated version of method 1 that also involves a right-hand side, so we'll have to do something about that first. So first, we're going to take the corresponding homogeneous differential equation by forcing the right-hand side temporarily to 0. This is in the form of a Cauchy-Euler equation if a is 1, right? Because I have second x squared term with the second derivative and x term with the x prime derivative. That makes b -3. And then I have no x's with the just y term, so c is 3. So here's my memorized form, am squared plus b minus am plus c equals 0. And so that means I have m squared plus -3 minus 1m plus 3 equals 0, or m squared minus 4m plus 3 equals 0, which is going to factor into m minus 1 times m minus 3. So again, I have two distinct real roots. So that means my complementary solution now, or my characteristic solution with the 0 here, is going to be a constant times x to the first power plus a constant times x to the third power, okay? And then we could use something like the methods from the last section, variation of parameters, to find to find the yp. So yp here is going to be instead some function of x times x and some function of x times x cubed. And we'll use our methods here that u1 prime is equal to the Wronskian using these functions. So that would be x cubed 1 3x squared, right? And then on the top, we're going to have to leave this column alone, x cubed 3x squared 0, and then we have to replace with the right hand side. But you got to be really careful here because, right, it's not this. You first have to divide everything by this, right? Because this works when it's in the form where you've got a 1 here. So the real right hand side function is actually 2x to the fourth e to the x over x squared. So it's really only 2x squared e to the x, okay? So that's what I'm going to plug in here, 2x squared e to the x. Okay, so let's find these Wronskians. The Wronskian down here is 3x cubed minus 1x cubed. And then on the top we have 0 minus 2, and then it's going to be x to the fifth e to the x, right? So this is just negative 2x to the fifth e to the x over 3x cubed minus 1x cubed is 2x cubed, which this would cancel a little further, and we would end up with negative. The 2's cancel. This cancels all but 1, so we have x squared e to the x, right? Negative x squared e to the x. Okay. While we're at it, let's go ahead and find the u1 by taking the antiderivative of that. So negative x squared e to the x. This one's going to require by parts probably twice. So let's use, first of all, u equals x squared dv is e to the x dx, which means du is 2x dx, and v is e to the x. So the uv minus v du would be x squared e to the x minus integral of e to the x, and then du is 2x e to the x. So we've got x squared e to the x minus, I can bring the 2 out. Now I have an x e to the dx. Let me change colors here for a second, and we'll do the inner one. Use purple here. So I'll do by parts again on this. So let's make ux and dv e to the x, so that du is equal to dx and v is equal to e to the x. So uv minus integral of v du turns out to be x e to the x minus, and the antiderivative is e to the x. So this is going to replace this right here. So we have to multiply by negative 2. So the result of that is that u1 turns out to be this term, x squared e to the x. Okay. Let's see, minus 2 times this, which is x e to the x minus would be plus 2 e to the x. However, this is the result of this, and the whole thing was negated. So in fact, it's the negative of that. It's negative x squared e to the x minus 2x e to the x plus 2 e to the x. And each term is a little different here. We have an e to the x, an x e to the x, and an x squared e to the x. Okay, so that's u1, and that's what we're going to end up substituting here. Now we got to work on u2. So u2 is the same kind of structure here. Let me use a different color. The same structure here for u2 prime. I'm going to move that down, I think, a little bit. Let me do it down there. So u2 prime would be the same Wronskian down here, which is going to turn out to be 2x cubed. And then on the top, we have this Wronskian, but with this column replaced. So we're going to have the original x1 here, and then 0 and the 2x squared e to the x here. So we'll have, let's see, this is going to be 2 and then x cubed e to the x minus 0, which means this ends up being just e to the x. That's nice because that means that u2 is just the integral of e to the x dx, which is also e to the x. So that was easier to find this. And now that we have that, we can write our particular solution out. Yp is the u1, which is this thing here. So we've got negative x squared e to the x minus 2x e to the x plus 2 e to the x. And then that whole thing is times an x plus u2, which is e to the x, right, times x cubed. And then that means that let's see if there's any cancellation here. If I multiply this out, I get negative x cubed e to the x minus 2x squared e to the x plus 2x e to the x plus e to the x cubed. But we have an e to the x cubed and a negative e to the x cubed, so those things cancel. All right, so now we can write the general solution. The general solution is the complementary solution, c1x plus c2x cubed, plus the particular solution, which will be just this now, minus 2x squared e to the x plus 2x e to the x. There's our final solution there. Okay, so that was method one. This got more complicated because we had a right-hand side. Okay, let's do another example. And for this one, let's use method two. Okay, so we'll do this one with method two. Method two involves a whole bunch of memorized substitutions. So this is a Cauchy-Euler, right? Second derivative has x squared, first derivative has x, the no derivative has no x. Then we have some right-hand side. So here's the substitutions. The main one is x becomes e to the t, which means that t is natural log of x. But then it also turns out that y primes have to be replaced with 1 over x dy dt, and y double primes have to be replaced with 1 over x squared, second derivative of y with respect to t minus first derivative of y with respect to t. Okay, this would be written down. I'm not expecting people to memorize this if we want you to use this on a test. All right, so let's carefully do all the substitutions here. We have x squared, and then y prime, we use this substitution, which is 1 over x squared d squared y dt squared minus dy dt. Okay, and then I have minus x times y prime, but y prime is 1 over x dy dt. Okay, and then I've got plus y. Equals natural log of x, but natural log of x, let's see, natural log of x, well, let's take what x is. This is going to be, on this right-hand side, natural log of e to the t, which means these cancel, so the right-hand side is just t. And the reason this particular substitution works is because it will always be true that this 1 over x cancels off, 1 over x squared cancels, the 1 over x cancels, and you'll be left with just the derivatives, everything changed to t. This, actually, I made a mistake here. This is a t, dy dt. Okay, so the result here is we have second derivative of y with respect to t minus first derivative of y with respect to t minus another first derivative of y with respect to t plus y equals t, or y double prime minus 2y prime plus y equals t. Okay, so with this substitution, we end up getting a second order linear differential equation now with constant coefficients, which means I could go back to our earlier plain old auxiliary equation, right? I can say this is just m squared minus 2m plus 1 equals 0 and solve for that. Okay, so that would be m minus 1, m minus 1. So we have m is equal to 1 twice. And so in this version, we had that we use c1 e to the 1 times x plus c2. And since we have a repeat, we do x e to the x, if you recall. Okay, except in this case, it's not x, it's t. So let me erase that because we should be using the independent variable t here. We've changed to t. So this would be that yc is some constant times e to the 1 times t plus c2t e to the t. Okay. All right, so that's the homogeneous equation where we found this. Now we have to go back and find the solution for the particular equation. Could we do that with a table? Let's see if that's in the table. If you bring up the table for that, let's see. Right now we just have a t here. I don't have it handy in here. I should, but if you go and refer to your notes, it turns out that the expression for a table is that you make, or for just a variable like x in the table says for x, try ax plus b. So you get that from your table, and that means that we're going to postulate that the yp solution is ax plus b. Okay, so if that's true, then that means y prime will be a, and y double prime will be 0, right? And then if I put this into the differential equation, and remember, I'm working with this one now, okay? So I would say y double prime is 0 minus 2 times y prime, which is a, plus y, which is ax plus b, is required to be equal to t. So I keep reverting this, but this should be a t here because we're using t's. Okay, so then I've got some constant terms, negative 2a plus b, and then I've got a term of t, and so the system says that negative 2a, right, my negative 2a plus b must be equal to 0 because there's no constant, but my a has to be 1 to match. So if a is 1, and then negative 2a times 1 plus b must be 0, then that means b must be 2, right? And so that means my particular solution is going to be ax plus b, or at plus b. It's really a t. So it'll be 1 times t plus 2. And then that means my general solution now, y is c1 e to the t plus c2 t e to the t plus t plus 2. Okay, that's the solution to this differential equation, including handling the right-hand side. Now, the last thing we have to do is we have to undo the substitution by replacing t with the natural log of x, right? If x is e to the t, then t is the natural log of x. So the final solution here would be c1 e to the natural log of x plus c2 natural log of x e to the natural log of x plus natural log of x plus 2. Right, which these cancel and produce c1x plus c2x natural log of x plus a natural log of x plus a 2. And that's the solution. Okay, so you can kind of see why in the other procedure, the special t cases where we have to multiply extra terms are the natural logs, because that's what happens when you do a t here across the substitution boundary, is you get a natural log term out of that instead. So this is how you would do method 2. Okay. Okay, so that should be enough examples to get things done. The only thing left in the notes is just a summary of the whole chapter 4, higher order derivative system. So the first the first part there just says we have some procedures we can use, and just like in chapter 2 for first order, for higher order derivatives, the first thing you can ask is, do you happen to have a second order linear equation, differential equation, and you already have a solution and you need a second one? So if you already have a solution, then you can use that solution times u to find another solution, take the derivative, substitute, and solve to get u. So that's called reduction of order, and that's when you already have one solution, you need the second one. Okay, if that's not true, then you could say, well, do we have a homogeneous equation, so 0 on the right-hand side, with constant coefficients? If that's true, then you can use the auxiliary equation here, and then for a single root, c1 e to that root. For repeated roots, you just keep tacking on x's along with the e to the mx term. And if there's a complex pair, it's the constant times e to the real part x times cosine of the imaginary part x, and then another term with sine. Okay, if that's not true, where we don't have constant coefficients, then you can try the Cauchy-Euler form. Look to see if it's in Cauchy-Euler form. If it's in Cauchy-Euler form, where they match, the x squared matches the double prime and x for the prime term and so on, then you can use the alternate auxiliary equation for Cauchy-Euler and use the alternate version of roots here, right? Or you can use method 2, but I'm just going to put this one on here. Now, if none of those methods work, then we're going to need something from future chapters. We're going to continue to learn more things that work for the things that we haven't covered yet. Okay, and then there were a couple other things in the unit here too. We also know that if we want to check if two solutions are linearly independent, we can use the Wronskian, which means you load up all the functions for each of the solutions. You take all their derivatives to get a square matrix. And as long as that is not zero, then that means that they're linearly independent. Okay. And then we have two procedures basically for finding the solution if we have a right-hand side that's not zero, if we have a non-homogeneous differential equation. We first solve for the corresponding homogeneous solution, and then typically we divide by this a here to get a right-hand side. And then we either use the method of undetermined coefficients, where we look up the particular form in a table and then plug in and establish these constants, or we can do variation of parameters, where once we have the homogeneous solution, we just assume that the particular solution is the same functional part of the term, but times new functions u1 and u2. Right? You have to divide by the leading coefficient to get a new right-hand side. And then you use that the derivative is equal to the Wronskian on the bottom, and then the Wronskian with the row or the column replaced with zero and the right-hand side corrected function. And then you integrate to find the u's. All right, so those are all the procedures from chapter 4 that work with higher order differential equations that we've learned so far.